Welcome to a new Energy Capital interview. I'm Ana Tafoya, and today we'll be talking with Steve Hendrickson and Harrison Perrin. Steve is president of Ralph B. Davis Associates, an Opportune LLP company. Hi, Steve. How are you today?
Hi, doing fine. Thanks for having us.
That's great to hear, Steve. Also with us is Harrison, Petroleum Engineer with Ralph B. Davis. Hi, Harrison. How you doing?
Hi, I'm doing great. Thank you. Thanks for having us.
Great, Harrison. Doing this interview with me is Aldo Santillan, Managing Director and Editor-in-Chief of the Energy Capital magazine. Hi, Aldo. How are you?
Hi, Anna. Thank you very much. And especially thank you, both of you, Harrison and Steve, for this time with us.
In this interview, Harrison and Steve will talk with us about the differences, but mainly the similarities between two quite different, at first glance, energy-related processes: underground natural gas storage and deep saline injection of CO2. They'll also share with us why is it important to acknowledge their similarities, mainly in the case of carbon capture and storage technologies, in order to advance their large-scale deployment. So I'll start with our first question. First, what is underground natural gas storage? And on the other hand, what is deep saline injection of CO2?
Well, underground natural gas storage is a lot like what it sounds. It's injecting gas into underground formations primarily in order to store it for it to be used later. You know, it's a pretty old technology. It's probably been around, I guess, I'd say certainly since the 60s, maybe a little bit prior to that. And the purpose of it was to be able to take gas that had been produced but was not yet needed and store it for a time that it could be used. A great example would be for winter consumption for heating, for instance, where the demand goes way up. It's great to have some in storage in order to be able to meet that demand when the cold weather comes.
Steve, in that sense, what are the main similarities between these two activities in terms of their phases of development? Talking about instance, feasibility, modeling, operation, monitor, and closure.
Well, you know, as you could imagine, there's a lot of similarities because basically what we're doing is we're injecting a fluid underground and we want to store it there for a period of time. Now, in the case of CO2 sequestration, we want it to stay there forever. So that's one of the main differences. But in terms of engineering, we want reservoirs that have many of the same characteristics, right? We want them to have adequate storage capacity. We want them to be at a depth that allows us to utilize pressure in order to compress more gas and store it in the formation. Of course, to be able to contain that higher pressure, the reservoir needs to be deeper. We want to be able to get the fluids in fairly quickly, right? Because it would not do us much good if we had a reservoir to store CO2 in, or gas for that matter, but it took us a long time to get it in, right? So in the case of natural gas storage, we want it to go in quickly, but we also want it to come out very quickly. In the case of CO2, we want it to go in quickly and then stay in place.
Besides these characteristics of injecting CO2 in a permanent form, what would be the main differences between these two processes?
The main differences is the regulatory regime, right? Natural gas storage is primarily regulated at the state level, and currently underground sequestration of CO2 is, in most cases, with a couple of exceptions, is regulated at the federal level.
So the underground storage of CO2 is regulated by the EPA, and they actually have a special group that oversees the storage of underground storage of fluids. And so CO2 falls under a class 6 well, specifically CO2 storage. And there are a lot of regulations regarding the permitting process, the well construction, monitoring, and then eventually the site closure that natural gas storage sites are not subject to.
You know, as Harrison, she mentioned site closure there, and the question was raised, what are some of the comparisons between the two, between the two applications? And we know that in the case of natural gas storage, we really don't have this closure aspect to it, right? We're going to cycle gas in and out as long as the storage field is needed, and then eventually we'll just stop using it. On the other hand, CO2, it's been being placed in the ground and it's intended to stay there forever. And so there is some post-closure monitoring that occurs that is designed to demonstrate that the containment has, not been breached.
Right. And right now, for example, the EPA mandates that you have to monitor for 50 years unless you get special approval. So that's quite different from natural gas storage.
Going deeper on this legal and regulatory framework in the US, what will be the main difficulties for saline CCS companies compared with their counterparts in the underground natural gas storage side?
I think from a technical perspective, one of the challenges to CCUS is that we're generally looking at reservoirs that are saline bearing, salt water bearing, and therefore they were not, and probably have not been targets of hydrocarbon exploration. That means that they probably don't have any well penetrations. Very typically, we find that we're using old depleted reservoirs for natural gas storage. Those fields had wells drilled in them over time, and those wells were used to gather information about the reservoir that can be used to understand its storage capacity and how quickly fluids can move in and out. In the case of underground storage of CO2 in saline aquifers, we may not have any wellbore penetrations. And so the design process starts with more assumptions that then later get tested or validated when wells are actually drilled.
Right. I think that the biggest thing that natural gas storage has that CO2 storage doesn't have is that they've demonstrated that they can, safely store natural gas, and they've been doing this for years. Whereas because the CO2 storage is a relatively new technology, they just don't have this track record of success like natural gas storage does.
So in this sense, Harrison and Steve, what do you think are the factors motivating CCS technologies' large-scale deployment in the energy industry?
It's pretty well documented that there appears to be a pretty important shift in public opinion about the role that carbon dioxide emissions play in climate change. And that shift in public opinion is changing the political landscape. And that political landscape is creating incentives currently and clarifying existing incentives. And I expect we'll expand those incentives to have CO2 emitters place this underground. So that's the motivating factor. There's no economics behind it other than the incentives that can be created by the government, because there's really a fairly limited market for CO2. There is a market, but much of the CO2 that's emitted is in places where it would be difficult to get it to the market. And frankly, there's much more being emitted than we could ever use in industrial or commercial uses. So that's what's driving it. The challenge, though, is the cost side of the equation. And really the big cost part of the equation is in the capturing of the CO2. The underground injection and storage is it's expensive, but it doesn't tend to be the part that is variable with the emission source. So there's a variety of emitters that emit different concentrations of CO2. And concentration of the CO2 in the emission stream is one of the most important variables in petroleum. Basically, if there is a CO2 stream like from a power plant that is fairly dilute, it costs a lot of money to build and operate the equipment to purify that stream and then have a nearly pure CO2 stream that can be injected and stored. If you are emitting, say, from an ethanol plant, which emits pure CO2 as part of its ethanol process, then that capture cost is quite a bit less. In fact, it goes way down. In both of those scenarios, however, the cost of disposal, that is the transportation and the injection into the saline aquifer, probably wouldn't vary all that much. They're somewhat agnostic to the source because both of them are going to deal with a pure CO2 stream.
Why is it essential to develop analog studies between these two technologies and processes?
Yeah, well, as we mentioned at the outset, there really haven't been that many CO2 underground storage projects that have been implemented. And so just like any engineering problem, engineering builds on things that have been done in the past. So we find that underground storage of natural gas is a good place to start for some of the fundamental petroleum engineering considerations in order to begin the development of underground CO2 storage. So what do I mean by that? There's a whole geological study. There's this understanding of the structure of the reservoir, the porosity, permeability, the behavior of the fluids in that reservoir, and the ability of it to store fluids. How much pressure can it hold? Those things would be common between a natural gas underground storage and a carbon sequestration project. Also, in terms of injectivity of fluids, those are very critical design characteristics, things that have to be investigated through engineering equations and through reservoir simulation. And really, it's because of the strong level of similarities, underground storage of natural gas is a good launching point for the workflows that are needed to do a design of an underground CO2 sequestration project.
And I just wanted to provide some color on, the kinds of numbers that we're talking about in terms of natural gas storage sites versus these saline formations that are being used to store CO2. So currently in North America, there are approximately 500 natural gas storage sites, and that compares to 2 active CO2 storage projects in saline formations. So we definitely have a lot to learn from the natural gas storage that's been done.
Those of us that we are not engineers and we are not oil specialists, it calls attention that in the modern world full of digitalization, in the IoT era, analog studies are still important for the industry.
Yeah, I mean, it's not just this area, but I think that it's probably important to recognize that much of technological advancement, and certainly within the petroleum engineering world, tends to be one more of adaptation of existing technology. I think, a great example that a lot of folks who are outside the industry may not be really familiar with is hydraulic fracturing and horizontal drilling, right? We hear about the shale revolution, and if you were just a casual observer, you might think this is all brand new technology. But really, fracturing was invented in the 1940s. Horizontal drilling started in the 1920s. Certainly was very active from the 80s on. And it was really an engineering approach that combined those 2 technologies and then modified them and continued to refine them, that made them successful in developing shale reserves and the tremendous change in production that we've had. So, and that's a kind of a good comparison to what's happening here now with CO2 sequestration. In addition to a long history of natural gas storage projects, we've also got a long history of CO2 enhanced oil recovery projects, right? So those provide another source of information in terms of the properties of CO2, how it interacts with materials, how it should be handled safely, what it takes to work on wells that handle CO2. So we've got a lot of information already in the petroleum engineering repertoire, if you will, that we can pull together and start to solve these novel sequestration problems.